children. So this is the continuation of the chapter solid state, and in this part now we are going to understand certain numericals in the chapter, right? So first we will do the numericals based on formula making, right, which will involve simple formula making compounds and the compounds having voids in them, right, will involve the numericals involving the voids, octahedral and tetrahedral voids, right? So let us see the question now. So the question is given: a compound containing atoms A and B crystallizes in crystal structure. A are present at corners of cube and B are present at face centers. What is the formula of the compound? So the two elements A and B are there, and if we know the number of A and B, that is the ratio of the atoms A and B, then we can write the formula of the compound containing A and B. So what is the first step? First step is to find the number of the elements A and B in the compound, right? Now we know the number of A. A are present at the corners of the cube. So when they are present at the corners, you know, in a cubic cell, how many corners are there? 8. And the contribution of each corner is 1 by 8. Okay. So that means number of A are present at corners, and how many corners are there? 8. And contribution of each one of them is 1 by 8. So that makes number of A equal to 1. Similarly, B. Now number of B are present at face centers. How many face centers are there in a cubic unit cell? 6. And contribution of each is 1 by 2. So that makes it 3. So number of A is 1 and number of B is 3. So the formula is AB3. Right? So simply what we are doing is we are finding the number of A and B and we are writing the formula. Let us see another question. In this compound, which is again in a cubic structure, X are present at corners and Y at the body center. Now you have to give the formula. Now again you have to find the number of X and Y in the compound. So you see, number of X is, since X are present at corners, so there are 8 corners, contribution of each is 1 by 8, so that makes number of X equal to 1. Similarly, number of Y are present at body center. There is one body center in the unit cell and contribution of it is 1. So that makes it 1. So number of X and Y are 1 each. So the formula is XY. So this is the simplest type of formula, numericals that comes on formula making. Let's see the third kind of questions on formula making, which are based on octahedral and tetrahedral voids. Let us see the question now. A solid containing A and B, A are arranged in CCP way, right? A are arranged in CCP way. CCP means cubic close packing way. And atoms B occupy all the octahedral voids and half of the tetrahedral voids. You have to give the formula. So you see, in the solid, elements A and B are there. Now before you proceed, you should understand and remember that the atoms A are arranged in CCP way. That means atoms A, right? It's actually the anions who are arranged in a particular way, CCP or HCP, and it is the small size cations actually which occupy the voids. So probably in this question, A are the anions and B are the cations which are going into the voids, right? So first we will find out the number of A and B, their ratio, and then we will find out the formula, right? So you see, what are they saying? A are arranged in CCP way. So let number of atoms A is n. Suppose A is n. Now you know, as many are the number of spheres, that is the anions in the compound, that many are the number of octahedral voids, and twice of that number is the number of tetrahedral voids. This already we have studied in the voids part of the chapter, right? So since atoms A are n, then octahedral voids are equal to the number of spheres, that is n, and tetrahedral voids are twice of the spheres, that is 2n. Right, this already we know. Now we have to find out number of B. Now B are occupying all the octahedral voids. So let us find out number of B. Number of B is, they are occupying all the octahedral voids. So number of B is n, octahedral voids are n, plus they are also occupying half of the tetrahedral voids. Now how many tetrahedral voids are there? 2n. And how many are B? B are occupying half of the tetrahedral voids. So 1 by 2 into 2n. So total number of B is n plus half of tetrahedral voids, that is 2n. So that makes it 2n. So number of A is n and number of B is 2n. So the ratio of the atoms A and B is n is to 2n, right? That means 1 is to 2. So the formula is AB2, right? So this is how we find out the formula using the voids concept, okay? Let's see another question related to this part. So let us see the another question on the voids part, and that is, in an oxide of aluminium, the oxide ions, that is O2 minus ions, are arranged in HCP way. So you could see here it's the anions who are arranged in HCP way, right? So there is an oxide of aluminium, and in that oxide ions, which are the anions, are arranged in HCP way. And aluminium ions, that is the cations, are occupying the voids. Now how many voids, what kind of voids are these aluminium ions occupying? So you see aluminium ions occupy 2/3 of octahedral voids, right? And what is the formula of the oxide of aluminium? So let us start. We will find out the number of aluminium and oxide ions, and then we can find out the formula of the oxide. So since oxide ions are occupying or are arranged in HCP way, so let us suppose number of oxide ions is n. Now when the number of spheres or the oxide ions are n, then you know that octahedral voids are equal to the number of anions. How many anions are there? N. So octahedral voids are also n. And how many are the aluminium ions? Aluminium ions occupy 2/3 of octahedral voids. So aluminium ions are 2/3 of octahedral voids. So that makes it 2n by 3. So what is the ratio of aluminium oxide? Number of aluminium ions are 2n by 3 and oxide ions are n. So what is the ratio? This is the ratio. When you solve it out, what do you get? Al2O3. So the formula of the oxide is Al2O3. So after this, now let us come to another type of numerical that you get in the chapter, and that is related to the size of the cation, right, which fits into the void, octahedral or tetrahedral void. Let us see the type of question you get on this part. So there is a solid A plus B minus. It has NaCl type of structure, right? Radius of anion in this structure in the solid is 250 picometer. What is the ideal radius of cation? So they are saying that a solid AB has NaCl type structure. So you should remember that NaCl has octahedral type of structure. This you should remember, right? So when a solid is having octahedral type of structure and the radius of anion is given 250 picometer, then what is the radius of cation? What should be the ideal radius of cation? Let's see the solution of this question first. Let us see here. So you see that for N, since NaCl is having octahedral structure, for an octahedral structure, right, the radius of an octahedral void is given by 0.414 into radius of the sphere or anion, right? So what cation will occupy the void? Which void? Octahedral void, because the solid is having octahedral type of structure. So the radius of void, octahedral void, is 0.414 into radius of anion or the sphere. Radius of anion is 250 picometer. So the ideal radius of cation is 103.5 picometer, right? This is the ideal radius of cation, which would uh, exactly fit into the octahedral void, right? So to find the ideal radius of the cation, let us find the ideal radius of the void first, because it's the cation who is going into the void. So the void, octahedral void, has the radius 103.5 picometer, and this should only be the ideal radius of cation which has to enter into this octahedral void. So this is the answer of the first question. The ideal radius of the cation should be 103.5 picometer. Let's come to the second part. Now they say that can a cation of radius 180 picometer slip into tetrahedral site of this solid? Now what are they giving? They are saying that if a cation have a radius 180 picometer, can it fit itself or slip into the tetrahedral void in this solid? Now if we want to know whether this cation can fit or slip or get into the tetrahedral void, we should first know the radius of the tetrahedral void, right? Then only we will be able to understand whether the cation of this size can enter the tetrahedral void. Now for tetrahedral site, right, what is the ratio? You know that for tetrahedral site, the radius of void and radius of sphere, right, they should be in the limit 0.225 to 0.414. This part we have already done in the previous session, right? For tetrahedral site or for the tetrahedral structure, the radius of void, and who is going into the void? The cation. And the radius of sphere, that is the anion, should be in this limit, right? Now let us find the radius of the void, because it is the cation who has to enter into this void. So if we find the radius of this void, we would ultimately come to know what should be the radius of the cation. So we find the radius of void, the lower limit and the higher limit, right? So radius of void will be r sphere into 0.225, this is with the lower limit, and r sphere into 0.414, this will be the higher limit, right? So r, this is the sphere, radius of the sphere, that is the anion, and you know the radius of the anion is given 250 picometer, right? So 250 into 0.225 to the higher limit is 250 into 0.414. So the value comes out to be 56.25 to 103.5 picometer. So if the cation has a radius in this range, right, it can enter into the tetrahedral void, and if it has larger radius, then it cannot enter. What is the radius of the cation given? It is 180 picometer, which is more than the higher limit, 103.5 picometer. So the answer is no. The cation of 180 picometer cannot enter into the tetrahedral site because its radius is more than the required, right? So this kind of questions, they do come in solid state, children. Go through them. Let us wait for the second session now, the next session of the chapter, in which we'll be doing the rest of the part of the chapter. Goodbye.